look at this problem. Air is being pumped into a spherical balloon so that the volume is increasing at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, if I'm just reading that, it seems like I'm giving you a lot of information and it seems like we really have nowhere to start. But we do. We know we have a spherical balloon. What's that mean? Okay, so we have a circular balloon. All right, so what's happening is we are blowing up our balloon. Now, there's really not necessarily a lot to label here, but here's our balloon. As we put air into it, it's getting bigger. If I'm talking about how the volume increases, what is that? Rate of change. You'll also notice if you just look at units, if it's something per unit of time, something per second or per minute or per hour, that's a derivative. Cubic centimeters, cubic is always volume. So dV dt, I can get that by looking at how the volume is changing or looking at my units. It's getting bigger, so it is positive. All right. How fast is the radius increasing? If I want to know how the radius is changing, what am I looking for? dr dt. I'm not asking what the radius is equal to. I want to know how it's changing. So a rate of change is a derivative. When the diameter is 50, okay, if I'm talking about volume of sphere, you may not know this off the top of your head, but volume is 4/3 pi r cubed for a sphere. And I think I did put a blank slide next to these to give you a little more space. So that's my formula. Is there any mention of diameter in this? No. So diameter is all the way across. What can I get from that? My diameter is...
Your radius, because it's just 25.
Yes. Okay, here's the first question. Is the radius always 25? No, so I can't plug that number in yet. So I drew a picture. You may or may not need that here. But this is what I'm really looking for. Did you write down all the stuff you were given? I'm going to give you points just for doing that, making a list of what you have. And we have a formula. So now let's do the derivative. We're doing the derivative of everything with respect to time. So every variable gets d something dt when we do the derivative. So the derivative of v becomes dv dt. Okay, 4/3 pi, that's just my coefficient. So you bring your 3 down. 3 times 4/3 pi is 4 pi. R squared. But I did the derivative of r, so we get dr dt. That's our implicit differentiation. Now we just plug in stuff. dv dt was 100. It's 4 pi, my radius is 25 squared. dr dt. Okay, I'm not necessarily giving you nice numbers, so feel free to grab a calculator if you need it on these. So 25 squared times 4, 500 pi dr dt. So to get dr dt by itself, we divide by the 2500 pi. So that goes on the bottom to be 1/25 pi. I would like for you to include units on this, and you can get it right here from your good labeling. R, what was R measured in? Centimeters. Per. T is time. What was time measured in here? So it tells us at that particular instant, the radius was increasing by 1/25 pi centimeters per second. The next one, I want you to take a second and read it. I gave you an equation. I haven't given you any numbers to plug in yet. I want you to read the question and see if you can do your derivative. So, x of t and y of t are the x and y coordinates at time t of a point moving around this circle. Okay, so basically we have a circle and there's just a point that's constantly moving around it. If I ask you to do the derivative of this circle with respect to time, what's the derivative of x squared? What would I need to put with it if I'm doing it with respect to time? It's going to be a long day.
I was gonna say.
All right, derivative of y squared? And derivative of 25. Good. Did we get that part? All right. So it's because I did it with respect to time that it's not just 2x. We have to have that dx dt with it. So then, second part, I gave you x, y, and dx dt. So 2, my x is 3, dx dt is 12, plus 2, y is 4, we don't know dy dt. So I'm just plugging those into my equation. Subtract over 72. And divide, and we get negative 9. I didn't have any units here, so that would be my final answer. So just negative 9. Which, kind of makes sense. If you think about it, this is like a circle centered at 0, 0 with a radius of 5. If x is increasing, so I don't necessarily know where I am on the circle, but like as I'm moving here, my x's are getting smaller, right? My x's are still getting smaller. So if it's increasing, my x's are over here from rotating. And when I look at it, if my x is getting bigger, what's happening to my y value? It's getting smaller at that particular point. All right, any questions there? Let's look at another one. A rocket that is launched vertically is tracked by a radar station located on the ground 3 miles from the launch site. What's the vertical speed of the rocket at the instant that its distance from the radar station is 5 miles and the distance is increasing at a rate of 5,000 miles per hour? That's kind of confusing, isn't it? So what do you think we should do? Draw a picture. We have a rocket that's launched vertically. So that means we started here, we launched it, so the rocket is going up. It's tracked by a radar station located on the ground 3 miles from the launch site. So on the ground, 3 miles away, this is my radar station. If you need to, you can label what's what. I want the vertical speed of the rocket at the instant that its distance from the radar station is 5 miles. How do I measure how far the rocket is from the radar station? Okay. So in my picture, first, I need to label anything that's changing with a variable. Anything that stays the same can be that number. Is there anything that does not change in this problem?
3 miles.
Yes. The distance between the launch site and the radar station is 3 miles. That doesn't change, so it doesn't need a variable. But the rocket is going up, so that's changing, so that can be a variable. And as it goes up, this distance changes, so that can be a variable. Now that I have a picture and I have my variables, I can go through and look at what I'm given. I want the vertical speed of the rocket. What variable would that be?
5,000 miles per
Well, that's one of my speeds. So I'm asking, like, what would I call this? The vertical distance is x, so what would be the speed? I want the speed of x. That's how x is changing. So that is the derivative of x in terms of time. So dx dt. I asked, what is that vertical speed? So I don't know that piece. So my dx dt is what I'm trying to find. At the instant that the distance from the radar station is 5 miles, so the distance from my rocket to my radar station is 5. So I'm looking at the particular instant when y is 5. And that distance is increasing at 5,000 miles per hour. So what would my 5,000 represent? What variable would I call that?
dy.
Mm-hmm. That's how the y is changing. So dy dt is 5,000. Okay. We already said in the triangle Pythagorean theorem is our option since it's a right triangle. So x squared plus 3 squared equals y squared. You can write it like that. You can go ahead and change your 3 squared to a 9, whatever you like. All right, so derivative of x squared would be 3 squared, or 9. What's the derivative of that? 0. Equals derivative of y squared. What would that be? My thing just froze. Technology is not my friend today. Okay, so now we can plug in what we have. But you'll notice I have y and dy dt. I'm looking for dx dt. So if I'm going to be able to solve this, I have to know what x is. I didn't tell you x. Is there any way to figure it out?
Can you just, since you know y, can you see 3 squared as x squared?
Yeah. The particular instance I need, the y is 5. So I can do x squared plus 3 squared equals 5 squared. So at that instant that I'm looking for, my x is 4. And the reason I didn't plug that in before my derivative is because it changes. The only numbers you plug in before your derivative are ones that never change. All right, so now we can plug in all of our stuff. So we have 2 times 4, I don't know dx dt, equals 2 times 5 times 5,000. $6,250. X was our height, that was in miles. T was my time, which in this problem was given in hours. So my rocket is traveling 6,250 miles per hour. How are we doing with that one? Let's try one more, and then we'll be done for today. So we have a ladder, 10 feet long, rests against a vertical wall. Let's draw a picture. So I have my wall, the ground, and the ladder is right here. Does the length of the ladder change? No, so I can go ahead and just call that 10. It doesn't need to be a variable. If the bottom of the ladder slides away from the wall, so if the bottom is sliding away at a rate of 1 foot per second, how fast is the top sliding down? Okay, so if the bottom is coming out, the top's going to be sliding down. If I'm talking about rates, I need variables here. So I'm going to call these sides x and y. Okay, the bottom, that was my x, and its rate was 1 foot per second, so how would I label that? dx dt. That's how x is changing. If it's per second, it's always over dt. I want to know how fast the top is sliding down, so I'm looking for at the point when the bottom is 6 feet away from the wall, so my x is 6. What formula would we use? Derivative of x would be 2x dx dt. Derivative of y would be 2y dy dt. 10 squared is 100. Derivative of 100? 0. Okay, so I know my x is 6, my dx dt is 1, but here's a problem. I don't know y, and I'm looking for dy dt. So what do we have to do? Yes, I need to know what my y is at this particular moment. Keep in mind, at that moment, my x was 6. I can do 6 squared plus y squared equals 10 squared. So at that particular moment, my y is 8. So if we solve, we get dy dt to be negative 3/4. Why is it a negative?
Because the height's up.
Yep, the height's coming down, it's getting smaller. Y, that was my height, it was measured in feet. Per t, my time was measured in seconds. So it's dropping 3/4 of a foot every second. Okay, any questions? So we will practice a lot of these. We'll probably spend at least 4 to 5 days on this, depending on how we're doing. So the homework, I'm going to try something different for this unit. I think I'm going to try to get away from the books for a little bit and do handouts on Classroom, see if you like that better or not. So I did type all of this and post it on Classroom for you, but this is the assignment for the next few days. So you're not doing, there's 12 questions, you're not doing 1 through 12 right now. You can do, I mean, you probably know how to do several of them at this point. Honestly, you could probably do the first 5, but I would shoot for like 3 questions would probably be a good number. 3 to 4 questions would be good for today.